With the same setting as before, let us try to find the probability of drawing a blue ball in the second draw, given that you drew a green ball in the first draw without replacement. By now, you have understood that since there is no replacement, the second draw becomes dependent on the first draw. In other words, the second draw is conditional on the first draw. Hence, the event becomes a conditional probability statement. Let's break it down further and mathematically define the conditional probability. If we break the conditional probability, we can define event A as the probability of drawing a green ball in draw 1 and event B as the probability of drawing a blue ball in draw 2. The only thing making B conditional on A is the act of not drawing with replacement. Mathematically, we can write it as PB-A or PB given A. The formula for P or probability B given A is equal to P A intersection B divided by probability of event A. You already know how to calculate P in A intersection B, that is the intersection of events A and B. Let's try to apply this formula to a problem that is here. Probability of A is equal to 5 by 20. Let's now calculate P A intersection B. The total number of ways we can draw a green ball in draw 1 and a blue ball in draw 2 is 5 cross 5, that is 25. The total number of ways of drawing two balls equal to 20 into 19 equal to 380. Hence, P or probability of A intersection B is equal to 25 divided by 380. Hence, probability of B given A is equal to probability of A intersection B divided by probability of A, which is equal to 25 by 380 into 5 divided by 5 by 20, which is equal to 5 by 19. If you just try to solve the problem as a simple word problem, you'll get 5 by 19 as the answer, since you know that you already have 19 balls left when you draw a green ball in first draw, and you have 5 blue balls left in the bin. Well, that was easy, wasn't it? However, let's solve another problem with which we ended in the previous video. What is the probability of drawing two yellow balls without replacement? To solve this, we can define the events as event A as the probability of drawing a yellow ball in draw 1 and event B as the probability of drawing a yellow ball in draw 2. Now, drawing two yellow balls is probability of A intersection B. Since we are doing this without replacement, we can use the conditional probability formula to calculate this. By rearranging the formula, that is probability of B given A equal to probability of A intersection B divided by probability of A. That is, we get probability of A intersection B equal to probability of B given A into probability of A. In this case, we already know that probability of A is 4 by 20. Now what is probability of B given A? This is the probability of drawing a yellow ball in the second draw, given we have already drawn a yellow ball in the first draw and not replaced it. So we have 19 balls left. Since we have already drawn a yellow ball, 3 yellow balls are left now. Hence, probability of P given A is 3 by 19. So we get P A intersection B equal to 4 by 20 into 3 by 19, which is equal to 12 by 380, or which is equal to 0.032. You can check that this is what you got earlier as well, when we try to solve it more intuitively than rather using the formula of conditional probability. Let us end this discussion or this video with two interesting points. First, you look at the formula of P or probability of intersection B for dependent and independent events. The only difference is that probability of B gets replaced with probability of B given A. Second, the condition for the conditional probability formula, that is probability of B given A equal to probability of intersection B divided by PA. For this formula to work, the condition is that the denominator is non-zero, that is PA is not equal to 0. In this video, you learn the addition rule of probability. Let us begin with a simple word problem related to Venn diagram, which you might have solved at some point in our life and other discussions. Let us consider that in your city, which has 100 households, there are two newspapers that are published, the Times and the Daily News. The circulation department reports that 25 of the city's households have a subscription to the Times and 35 subscribe to Daily News. A survey reveals that 6 of all households subscribe to both newspapers. How many of the city's households subscribe to either newspaper? Let's start the solution and discussion pertaining to that. You know that this can be easily represented as the Venn diagram shown here on the screen. Notice the formula. Probability of A or B equal to probability of A plus probability of B minus probability of A and B. if A and B are mutually exclusive events, then this probability of A and B is equal to 0. Here, A is the number of households reading the Times and B is the number of households reading the daily news. The shaded region that overlaps A with B, that is A intersection B, indicates the households which have subscription to both. We already know that A is equal to 25, B equal to 35, and A intersection B equal to 6. Our objective here is to find A union B. Now let's divide the three regions as a small a, those who read only the Times, small b, those who only read the daily news, and c, those who read both. Therefore here a is equal to a plus c, which is equal to 25, b equal to b plus c, which is 35. We know that a union b equal to a plus b plus c, which is a plus c plus b minus c plus c, which is simple arithmetic, and you get a union b equal to capital A plus capital B minus small c. In other words, the union of A and B, that is A union B, equal to A plus B minus intersection of A and B. In our case, this comes out to be as 25 plus 35 minus 6, which is equal to 54. Now if you divide these numbers by 100, you'll get the probabilities of the different events, that is P, or probability of A union B, becomes 0.54, P of A, which is 0.25, P of B, which is 0.35, and P of A intersection B, which is 0.06. When you replace the equation with probabilities, you'll get P, or probability of A union B, equal to P of A plus P of B minus P of A intersection B. Addition rule of probability can be understood using the image shown here. The intersection region is something we need to subtract. If A and B are mutually exclusive, then probability of A intersection B becomes 0. Joint and marginal probability. Now let us discuss different types of probability. The three major types of probability include joint probability, marginal probability, conditional probability. To understand joint and marginal probability, let us consider an example to know whether an MBA degree could be a possible factor in the success of mutual funds manager. The table here compares mutual fund performance against the rank of MBA programs from where the fund managers earn their MBA degree. Let's say we have the data of the performance of 400 mutual funds, and using that we create this table. Here we have created the table such that the data is divided in 4 parts. This is known as contingency table. On the left margin, we have the fund managers who graduated from a top 30 MBA program and those who did not graduate from the top 30 MBA programs. On the top of the table, we have divided the mutual funds based on whether they have or haven't outperformed the market. This can also be represented in another way as shown here. If you look closely, this is very similar to a two-step experiment where the first experiment is the fund manager graduating from a top 30 MBA program and the second experiment is fund outperforming or not. This is quite similar to what we did in the machine learning project completion example, which was also a two-step experiment. Now before we calculate different types of probabilities, we need to first convert this into a probability table. To do that, let us divide all the values by 400, as that is the total number of data points that we have used. That gives us the following table, as we can see here on the slide. The value 0.1 in the table means that of the complete data, 10% of the mutual funds were such that the fund manager had graduated from a top 30 MBA program and also that the fund outperformed the market. Such a probability is known as the joint probability, where we are calculating the probability of 2 or more events occurring simultaneously. This is also the same as calculating the probability of an intersection of 2 events. Thus, we can say that the joint probability that the mutual fund outperforms the market and the fund manager is from a top 30 MBA school is the probability of the intersection of these 2 events, which is 0.1 pair. As shown here on the screen, we also have given notations to each of the events for simplicity, where A1 is for fund manager graduating from a top 30 MBA program, A2 is for the fund manager that did not graduate from a top 30 MBA program, B1 is for the fund that outperforms the market, B2 is for the fund that does not outperform the market. Here we can write the joint probability of event A1 and B1 is equal to probability of A1 intersection B1, which is 0.11. Here we can write the joint probability of event A1 and B1, which is equal to probability of A1 intersection B1, which is 0.10. The joint probability of events A1 and B2, which is equal to 0.25. The joint probability of event A2 and B1, which is equal to 0.04. And the joint probability of events A2 and B2 is equal to 0.61. Next, let us understand the concept of marginal probability. What if I ask you to calculate the probability that a mutual fund outperforms the market? Can you answer this from the data provided to you? Yes, you can. The probability that the fund will outperform the market will nothing but the sum of all the probabilities shown in rows 1 and 3, which is equal to 0.1 plus 0.04, which is equal to 0.14 or 14%. What we have calculated here is the marginal probability. So basically, the marginal probability describes the probability of an event occurring irrespective of the knowledge gained or the effect from previous other external events. So once again, the marginal probability of B1 is nothing but probability of B1, which is equal to 0.14. Now let us try to calculate the probability that a mutual fund will outperform the market given that the fund manager graduated from a top MBA program. Is this a conditional probability problem? Well, yes, it is. And we'll use the following formula, which is probability of B1 given A1 equal to probability of A1 intersection B1 upon probability of A1. From the table, the probability that a manager graduated from a top MBA program is a marginal probability. Hence, probability of A1 is equal to 0.1 plus 0.25, which is equal to 0.35. We also know that the joint probability, which is probability of A1 intersection B1, from the table as 0.1. In other words, there is a 28.57% chance that a fund would outperform the market given that the manager graduated from a top MBA program. Let's close this discussion with one interesting lesson. What happens to the conditional probability formula if the events are independent of each other? In that case, probability of A given B equal to probability of A, since probability of A1 intersection B1 equal to probability of A into probability of B for independent events. This formula essentially states that the probability of A given that the B has occurred is independent of event B. Similarly, the equation for probability of B given A is equal to probability of A into probability of B will also hold true for the same reason. As an exercise, we can check if the event mutual fund outperforms the market and the event fund manager is from a top MBA school are independent of each other or not. So coming back to the conditional probability, our objective was to find the probability of an event taking place with the information that a previous known event had already occurred. Such scenarios are very common in the industry, and this is where Bayes' theorem comes into picture. In the next set of videos, we'll discuss the Bayes' theorem in the context of conditional probabilities. Bayes' theorem part 1. Let us go back to our earlier experiment where we were trying to understand whether the MBA degree could be a possible factor in the success of a mutual funds manager. So let us see what data we had with us. So to quickly recap this table, remember that 0.1 in the table meant that of the complete data, 10% of the mutual funds were such that the fund manager had graduated from a top 30 MBA program, and also that the fund outperformed the market. Now recall how in the previous discussions we calculated the probability that a mutual fund will outperform the market, given the fund manager graduated from a top MBA program. Let us quickly go over the steps here. We used the formula for conditional probability where we calculated probability of B1 given A1. For this video, instead of calling them B1 and A1, let's just call B and A events for simplicity. So the events are defined as event A is for fund manager that graduated from a top 30 MBA program, and event B is for fund that outperformed the market. And we said that probability of B given A equal to probability of A intersection B divided by probability of A. From the table that we have seen, we have probability of A intersection B as the joint probability of A and B, which is 0.1, and we calculated probability of A, that is PA, as 0.35. So substituting these values, we got the probability of B given A equal to 0.1 upon 0.35 equal to 0.286 or 28.6%. So this 0.286 is the probability that a mutual fund will outperform the market, given the fund manager graduated from a top MBA program. Now suppose I ask you the following question. What is the probability that a fund manager has graduated from a top MBA program given that the mutual fund outperformed the market? If you observe the table, you will notice that this is nothing but probability of A given B. So why don't we quickly calculate and see what this gives us? Using the formula about conditional probability that you learned earlier, we can write probability of A given B equal to probability of A intersection B divided by probability of B. We already know that probability of A intersection B equal to 0.1. What will be probability of B? Remember that B is the event that mutual fund outperformed the market. So if we go back to our table, we can see that B will be the sum of rows A, 1 and 3, which is equal to 0.1 plus 0.04, which comes to 0.14. So putting in the values, we get probability of A given B equal to probability of A intersection B divided by probability of B, which is equal to 0.1 divided by 0.14, which is equal to 0.714. Now remember that before we calculated probability of B given A, and therefore we got the probability as 0.286. And when we calculated probability of A given B, we got the probability as 0.714. So let us write down both the equations here. Probability of B given A equal to probability of A intersection B divided by probability of A, which is 0.286. Similarly, probability of A given B equal to probability of A intersection B divided by probability of B equal to 0.714. Now, let us rewrite both these equations that we have here. In the first equation, if we multiply both the sides by PA, we can say that probability of B given A into probability of A equal to probability of intersection B. And for the second equation, if we multiply both sides by probability of B, we can say that probability of A given B multiplied by probability of B equal to probability of A intersection B. Now if you observe the screen, the right side of both these equations is exactly the same and is equal to probability of A intersection B. So if we equate these equations, we can write probability of B given A into probability of A equal to probability of A given B into probability of B. We can write this equation in different manners, noting that probability of B given A equal to probability of A given B into probability of B divided by probability of A. This equation is the most basic form of the Bayes theorem. In other words, you can say that Bayes theorem provides a way of relating different conditional probabilities. Now you might be wondering, what is the big deal here? All you did was some basic linear algebra and came up with some great looking formula. Couldn't we simply calculate P, that is probability of A given B, and probability of B given A using the table directly? In many cases, the joint probability formula of probability of intersection A and B is usually not known to us. That is, probability of intersection B is not known to us. In many practical scenarios, you may only have information about probability of A given B and some knowledge about the events A and B, using which you may want to calculate probability of B given A. This may not seem very intuitive at first, but we'll have a look at some examples in the next discussions. Bayes theorem part 2. So in the previous video, we learned that the Bayes theorem comes into picture when a direct calculation of a conditional probability is not possible due to lack of information. So let's take an example of such a case. This is one of the most common applications in the medical domain. There is a study going on to understand the likelihood of middle-aged women who develop breast cancer. So let's say that the past research suggests that the probability of a middle-aged female developing breast cancer is 0.01 or 1%. Let's name this event and call this event B. So probability of B PB equal to 0.01. Before we move on, let us ask a question. Do we think the medical tests that we do are 100% accurate? Do they always predict correctly? Well, the answer is the accuracy varies from test to test. But the breast cancer detection tests at times are incorrect. A person can be tested positive for breast cancer, but in actuality one may not have it. The vice versa is also possible. And these are the major types of misdiagnosis. We already know that PB equal to 0.01, where B is the event that a middle-aged female develops breast cancer. Now we want to know how this probability changes if the female tests positive. So basically, we want to find the probability that a female actually develops breast cancer if she tests positive. We cannot treat this as 100% because there can be cases of misdiagnosis as well. So in other words, we are looking or asking how reliable is this testing methodology. Can you tell what type of probability we are looking at here? This is a type of conditional probability because we are measuring the probability of breast cancer given the condition that the test came positive. So let's name some of these events to avoid confusion later on. Earlier we called the event of a middle-aged female developing breast cancer as event B. So let's call the event that a female tests positive as event A. Then the probability that we are interested in measuring is basically PB given A. To calculate this, we have decided to perform an experiment, and here are the results of that experiment. We have a sample of women who already had breast cancer and found that only 90% of these women tested positive. This means that the probability of women testing positive given she has breast cancer is 0.9. So what is this 0.9? Isn't this PA given B? Remember that event A is the event that a woman tests positive and event B is that event that a woman has breast cancer. So we have P of A given B is 0.9 and we wanted to calculate P of B given A. So let's see if we have all the information we need from Bayes rule. As per Bayes' rule, P of B given A equal to P of A given B into PB divided by PA. So we have P of A given B and PB with us, but now we need to calculate PA. PA is basically the probability that a woman tests positive. Now this information may not be available directly, but we have another piece of information that might help us. In our experiment, we also considered women who did not actually have breast cancer and found that 8% of these women were misdiagnosed and hence tested positive. So I can say that 8% or 0.08 is basically the probability that P of A given B dash. Think about this. B is the event that a woman has breast cancer. This means that B dash, which is the complement of B, will be an event that a woman does not have breast cancer. And we are measuring the probability that a woman will test positive given the condition that she does not have breast cancer. Hence, this probability is nothing but P of A given B dash. So let's play a little bit with our PA. It may get a little mathematical here, so let's try to understand each term that we talk about. We can say that PA can be expanded as P of A intersection B plus P of A intersection B dash is equal to PA. How did I get here? Remember the joint probability table, but this time let us put everything in terms of A and B. For example, as we can see here in the table, probability of A equal to P intersection A and B and P of A intersection B dash. Similarly, probability of A dash equal to probability of A dash intersection B plus probability of A dash intersection B dash. Let us not be overwhelmed looking at this table. We have just replaced all the joint probability values in their mathematical notation. For example, the joint probability of A and B is written as P of A intersection B, and the joint probability of A and B dash is probability of A intersection B dash. So how do we calculate the marginal probability of A? Marginal probability of A will be the sum of the values in column B and B dash. This is how we will get PA equal to probability of A intersection B plus probability of A intersection B dash. Now let's try to use our conditional probability knowledge to modify this equation a little bit. We can write probability of A intersection B as P of A given B into PB. And similarly, we can also write probability of A intersection B dash as probability of A given B dash into probability of B dash. So let's plug in these values and see what we get. We had probability of A equal to probability of intersection B plus probability of intersection B dash. And now we can write this as probability of A equal to probability of A given B into probability of B plus probability of A given B dash into probability of B dash. So if we plug this in the original equation, we'll get probability of B given A equal to probability of A given B into probability of B divided by probability of A. Now let us replace probability of A with the equation that we have derived here. So we get probability of B given A equal to probability of A given B into PB divided by probability of A given B into probability of B plus probability of A given B dash into probability of B dash. So let us see if we have the data to calculate probability of B given A. What are these A and B here? Event A is the event that women test positive and event B is the event that a woman has breast cancer. We already saw that we have probability of A given B equal to 0.9 and probability of B as 0.01. Now we are left with probability of A given B dash into probability of B dash. Remember that in the place of having information about PA, we instead had the information about PA given B dash, which is nothing but the probability that a woman will test positive given the condition that she does not have breast cancer. And we saw that this value is 0.08. So finally we are left with probability of B dash. This is simple. It will be nothing but the complement of B. Recall the complement rule here. Therefore, probability of B dash will be 1 minus probability of PB, which is 1 minus 0.01, which is equal to 0.99. So let's plug in these values and we have probability of P given A equal to 0.9 to 0.01 divided by 0.9 into 0.01 plus 0.08 into 0.99, which is 10.2% or 0.102. Hence, there is only a 10.2% chance that a woman will develop breast cancer if she tests positive. What did we make of the test? Yes, we are right. It's not reliable at all. So what did we learn in this video? We saw a simple example where we were able to make use of a few known conditional probabilities and calculate some new conditional probabilities. And we were able to do this with the help of Bayes' theorem, which is given by probability of B given A equal to probability of A given B into PB divided by probability of A given B into probability of B plus probability of A given B dash into PB dash. Now let us try to understand the significance of this equation. Generally, we start off with the set of initial prior probabilities. You can say that prior probability is the probability of an event before we did our experiment and collected our new data. In our case, the probability of event B, which was the probability of a female developing breast cancer, is the prior probability. This value was 0.01 or 1%, and we knew this because of our past. Then from certain sources, we obtained new information about all the events for which we had the prior probabilities. In our case, These sources were the experiments that we performed and got two important pieces of information about the relation between actually having breast cancer and being tested positive for breast cancer. This information was given to us in the form of conditional probabilities, that is, probability of A given B and probability of A given B dash. Our objective was basically to update our prior knowledge about females developing breast cancer with this new information and calculate PB given A. This new probability that we calculated is referred to as posterior probabilities, and Bayes' theorem is used for making these probability calculations. In our case, the probability that a woman has or will develop breast cancer if she tests positive was the posterior probability. Now this formula for Bayes' theorem is actually most basic form of Bayes' theorem because we are assuming that B is dichotomous, that we can only break it into B and B dash. And therefore, probability of B given A is equal to probability of A given B into PB divided by probability of A given B into PB plus probability of A given B dash into PB dash. However, in reality, that may not be the case. With this, we conclude this video where we saw the application of Bayes' theorem. Recap Bayes' theorem. So, we have learned that Bayes' theorem can be used to calculate posterior probabilities, and the formula is given as probability of B given A equal to probability of A given B into probability of B divided by probability of A given B into probability of B plus probability of A given B dash into probability of B dash. In the previous example, where we considered event B as the event where a female develops breast cancer, there were only two possible outcomes to this experiment. Either the female had breast cancer or that she does not have breast cancer, and the probabilities of these two events happening were denoted by PB and PB dash. But what if the experiment could have more than two outcomes? Let's say I break down B into B1, B2 and B3. Can I still apply Bayes' theorem in that case? Of course we can. Here we are presenting an interesting case study based on 3 hospital centers which are being subjected to a malpractice lawsuit. You have the information about a patient being treated in one of the 3 hospital centers. Let's name them Hospital 1, Hospital 2 and Hospital 3. And suddenly if we inform you that a malpractice suit has been filed, but we don't know which hospital has the lawsuit that has been filed. Lawsuit indicates malpractice and you do not want your patient to be treated at such a hospital. Hence, you decide to find the probability that this lawsuit was filed against which hospital, whether hospital 1, 2 or 3. To understand the problem better, let us look at the information that we have at hand. Let's say we are given the following prior probabilities. So let's consider event BI as the event that a patient treated at hospital I. Thus, the probability that a patient was treated in hospital 1 is PB1, which is 0.6. Similarly, the probability that a patient was treated in hospital 2 is PB2, which is 0.3. And the probability that a patient was treated in hospital 3 is PB3, which is 0.1. So these are our prior probabilities. This varies due to various factors like bed availability, number of recognized doctors, reputation, and various other factors. Now we have B1, B2, and B3 such that the probabilities of all these 3 events sum up to 1. Hence, in this example, B is said to be a polytomous in nature, while in our previous example, B was dichotomous in nature. Next, let us learn about the new information available to us. Let us say that the hospitals have shared the probability that a malpractice suit was filed against them in the past. This means that we have the conditional probability of a malpractice suit being filed given that the hospital is known to us. For example, if you see the table provided here, you can see that the probability that the malpractice suit is filed given it is hospital 1 is 0.002. The probability that the malpractice suit is filed given it is hospital 2 is 0.005, and the probability that malpractice suit is filed given it is hospital 3 is 0.007. So what is the objective of this problem? Let's say malpractice suit is filed today. Then what is the probability that the suit was filed against hospital 1? In other words, we want to calculate PB1 given A, that is probability of B1 given A. So how do we calculate this? Recall our earlier question of Bayes' theorem, which was probability of B1 given A equal to probability of A given B1 into probability of B1 divided by probability of A. Now remember that whatever problem you are given, you can always start from this formula and then derive the final equation from there. We already know that probability of A given B1 and probability of B1. What we don't have with us is probability of A. Probability of A is nothing but a marginal probability. We had created a joint probability table as we are seeing here, and we said that we can calculate the joint probability of A as probability of A intersection B plus probability of A intersection B dash. But now we have B1, B2 and B3. Again, we need to do is simply rewrite this table we have the joint probability of A and B1 as probability of A intersection B1, the joint probability of A and B2 as probability of A intersection B2. In this scenario, we have the joint probability of A and B1 as probability of A intersection B1, the joint probability of A and B2 as probability of intersection B2, and so on. Hence, the marginal probability of A comes out as probability of A equal to probability of A intersection B1 plus probability of intersection B2 plus probability of intersection B3. And we have already seen how to write any of the joint probabilities in terms of their conditional probabilities. So we can write probability of intersection B1 equal to probability of A given B1 into probability of B1, probability of intersection B2 equal to probability of A given B2 into probability of B2, probability of intersection B3 equal to probability of A given B3 into probability of B3. Hence, substituting these values back into probability of A, we get probability of A equal to probability of A given B1 into probability of B1 plus probability of A given B2 into probability of B2 plus probability of A given B3 into probability of B3. Now, let us say we want to calculate probability of B1 given A. That is, probability of B1 given A equal to probability of A given B1 into probability of B1 divided by probability of A. And we know that probability of A equal to probability of A given B1 into probability of B1 plus probability of A given B2 into probability of B2 plus probability of A given B3 into probability of B3. Hence, probability of B1 given A equal to probability of A given B1 into probability of B1 divided by summation of probability of A given B1 into probability of B1 plus probability of A given B2 into probability of B2 plus probability of A given B3 into probability of B3. Similarly, we can also write probability of B2 given A equal to probability of A given B2 into probability of B2 divided by summation of probability of A given B1 into probability of B1 plus probability of A given B2 into probability of B2 plus probability of A given B3 into probability of B3. Now let's see if we have all the values with us. We have probability of A given B1 as 0.002, probability of A given B2 as 0.005, and probability of A given B3 as 0.007. We also have probability of B1, B2 and B3. So what we get? Probability of B1 given A equal to 0.002 into 0.6 divided by 0.002 into 0.6 plus 0.005 into 0.3 plus 0.007 into 0.1 summation 3529 or 35.29%. This means if malpractice suit take place, know that there is a 35.29% chance that this suit took place against hospital 1. Now you can similarly calculate the probability of suit taking place at hospital 2. This is nothing but probability of B2 given A, and can also calculate probability of B3 given A. Now, why did we consider a problem where B could have actually been broken into B1, B2 and B3? The reason is that these scenarios are more common in the industry and real life, and that even though you may have seen a lot of complex calculation being made in this segment, Bayes theorem is not that complex, and you can actually extend this to a more complex scenario. Suppose we have multiple events such as B1, B2, B3, B4 and so on up to Bn, which are mutually exclusive. Simply modify the denominator of the right side of the Bayes theorem. If you are calculating probability of Bi given A, then probability of Bi given A equal to probability of A given Bi into probability of Bi divided by Pa. That is probability of A. Now, depending upon the number of events that you have, it could be B1, B2, B3, which means 3 events that could be B1, B2, B3, B4 and all the way up to Bn. Then you can generalize the Pa as follows. The generalized form of Bayes theorem comes out to be probability of Bi given A equal to probability of A given Bi into probability of Bi divided by summation of probability of A given B1 into probability of B1 plus probability of A given B2 into probability of B2 and so on up to probability of A given Bn into probability of Bn.